Okay, good morning everybody. Today is the second part of concurrency control. So this is a cheat sheet for last week. So what did we learn last week? We learned about transactions. So it bundled several SQL statements into an atomic operation. That is what a transaction is about. You will also see the concept of a transaction not only in databases but also in other parts of computer science. Then we had ACID. So these four letters mean atomicity. Atomicity, all of it is executed or none of it. So the transaction is an unsplittable unit. All of its actions are executed or none of those actions. That's very important. Consistency, meaning when the transaction starts, it expects the database to be in a consistent state. When the transaction wants to commit, it must leave the database in a consistent state. So consistency is defined through integrity constraints, for instance, or other consistency rules, foreign key constraints, primary key constraints, unique and stuff like that. But sometimes consistency is not mechanically defined in the system, but only by a human who looks at the data and sees, oh, the data is messed up, it's inconsistent. If you are in a situation like that, you should. If you find an inconsistency that's not phrased as an integrity constraint in the database, you should immediately add an integrity constraint. Isolation, that's the focus of these lectures last week and this week, is meaning, okay, from the point of view of the transaction, it looks like as if it owns the database. It doesn't see changes, it doesn't see actions from other ongoing transactions. And the analogy I had was, imagine you go to Mensa and you have the Mensa alone for yourself. No one else is in that Mensa. That is at least how it looks like from the point of view of the transaction. In reality, there are people in the Mensa. You have these glasses, Google glasses, that pretend there's no one there, but in fact it's crowded with people. And the database has to make sure that there are no conflicts. Then there's durability. Durability means once the transaction commits and the database signals back to the user that the transaction was committed successfully, the database system must never lose the data, must never lose the changes. And again, that's always a relative term because you can do as many copies if you want. If you lose all of the copies, you're screwed. Well, one other anecdote I can explain, tell you, I didn't tell it last time. So there was a famous video a couple of years back from a guy who was very proud, a developer, that he did so many replicas. So he had a laptop and he had two external hard drives on his desk. Yeah, so you always would be replicating the contents from the laptop to the two hard drives. Well, what happened? A thief entered his apartment and stole the laptop plus the two hard drives. So is the data durable? Depends on how you see that. From the point of view of the guy, not anymore, right? Because the data is gone. From the point of view of the thief, yeah, you actually even have 3 copies of the data. Fantastic, yeah? So it's a very subjective, durability is very subjective from your point of view. Actually, the video was really funny because there was a service on his laptop calling back to a domain service, and eventually the guy managed to find the thief and send the police, and then he got back the laptop and all the backups. There was a software developer. Maybe I can dig up the video again, I'm not sure. Okay, so, and then the question is, how do we do that? So how do we guarantee automatic isolation? That is the focus of this lecture. And these things are intertwined, of course. Yeah? So if you lose one of the properties of acids, you typically lose the others as well. Yeah? So there are dependencies in that. We talked about schedules, sometimes called a history. That is a concrete interleaving of read-write operations. So the atomic read in the sense of a select star from blah, 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 where ID equals 42. And versus a write being an insert, delete, or update in SQL, an atomic statement. Yeah? So how are they interleaved in a concrete schedule? And is that interleaving okay, or will that lead to problems? So we talked about that. So the optimal thing you can do in terms of correctness is a serial schedule. Yeah, if all transactions are executed one after the other, nothing can go wrong. Yeah, there's no interleaving, there's also no concurrency, no multi-threading, none of these problems. So that's the best you can do, but you will be losing performance, of course. Yes? You want to have concurrent execution. Then we talked about conflict serializable schedules. The major takeaway here is that in such a schedule, actions may be interleaved, However, the conflict operations are in the same order as in the serial schedule. So the intuition of that is, I mean, the problems that may happen in these concurrent schedules is only with respect to the conflict operations. And if you keep them in the same order, everything is fine. Yeah? Plus, the read operations must also return the same things, but we talked about that as well. Then we have the conflict graph, so that's an aggregated form of a schedule. Conflict graph is not per operation in a transaction, but per transaction. You have one node for each transaction appearing in the schedule, and then you draw arrows on whether there's a conflict operation or not. And then you can make a reasoning that if there's no cycle in the conflict graph, then the associated schedule is conflict serializable. Okay. Yeah, with that, let's switch to the notebook. So before we dive further into the theoretical aspects and how these algorithms work, so let's look at the user side of transactions. Here's a little notebook we prepared using DuckDB, the database we already used. In that lecture, so the main thing you need to do is, so we have this reset database function that basically prepares the database, establishes a connection, and creates a simple table with a bunch of tuples, 5 tuples to be precise. And you can use DuckDB in 2 different modes. One is you have a main memory database which will not create a file. That's this first option. Or you create it such that it will write its data to a file. Yeah? All the data stored in the relations will be mapped to a file. I mean, that's what all databases do at the end of the day. Yeah? If you want to persist the data, the database system sits between the application and the file system anyhow. Yeah? So at the end of the day, the database system has to store the data. So where is it going to store the data? Well, in some files. Yeah? So it's in between you and the file system. Yeah, and then you can query the database. Basically, you specify the database. You get a connection. Here we have a simple select statement in that line, and then you call execute with that statement. And that's a SQL statement you pass as a parameter, and you call execute on that connection. And then you call on that connection this fetch all command, and then you get all the results. Maybe we execute that. Why not? Right. Yeah, the query returned the following tuples, blah, 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 blah. You can also display that in a pandas data frame if you want. So pandas is a library that's very popular in the data science domain. There are all kinds of libraries that allow you to transform outputs and inputs to different libraries, formats, and whatnot. So DuckDB is actually very well integrated into all of these data science libraries. You can do that in read-only mode. That is what's demonstrated here. So you have an extra parameter, read-only equals true. Yeah, then you can't change anything in the database. You will get an error, the query failed due to the connection being read-only. Yeah, here, inserting would change, so not read-only. That's a problem. Yeah, so those are basic operations, basic statements you send to the database. What about transactions? That is explained here. So what we do is we open 2 connections, connection 1 and connection 2. And we can do that on the same database. So we are simulating concurrent access. And then on connection 1, we insert something into the database. And once that is done, we do a select. Yeah? And what we are seeing here is that when you send a statement to the database, it will be executed immediately. So what I explained to you last time, that you first accumulate all of these statements in the transaction and eventually you say commit, yeah, that's not happening here in this notebook currently. You're seeing that, no, whatever you send, like the insert, it's being executed. So you could basically understand that as each of these operations is like a mini transaction in a way. Every insert statement is a transaction in itself. Every update delete statement is a mini transaction in itself, but we want to do something different. We want to bundle multiple insert, update, deletes into a bigger transaction. Yeah? And how do we do that? For that you need this begin commit syntax. So that looks like this. So basically that's the beginning of the transaction, committing is the end of the transaction. And in between are these statements that you want them to be executed by the database system. And for that, you have to explicitly call begin on the connection. Yeah? So that's what we're doing here. Do I execute? Yeah, execute that one. Yeah, and then you have, again, two connections simulating two users. So on this one connection, you execute update, whatever, and then you start with a second connection and actually execute the same statement here. The select statement you execute on the second as well, and so forth and so forth. Yeah? And then you see the appropriate changes being executed. What you can also do is you roll back a transaction, which actually means from the user point of view, you call abort. Yeah? That's what we had in this notation. There was, in the schedule, so a transaction would either be ended by a C, a small c, saying it wants to commit, or a small a, meaning abort. And abort means, no, I changed my mind, I don't want to execute any of this stuff. Yeah? And in that situation, the database has to make sure that none of these things get executed. So these updates must not be executed against the database state. No one else is allowed to see those changes. So it should be as if the transaction never happened. That is what abort is. What abort is saying. Yeah, and that's what we do here. So the command for that is rollback. Yeah, that's the same as abort, but telling the database, hey, don't forget about that transaction. Yeah, then you see it here, right? Okay, so that is how transactions are used from a notebook. If you later on, if you talk about web applications, we will be doing that next week. Then you will see there are other commands, but what is meant is always the same thing. Yeah? So you wrap multiple actions into a single atomic operation. Okay, so that is the agenda for today. So those are possible isolation problems and their solutions. We will be looking at those first three problems for now, and then advance through this agenda. So I don't have to go through that for the moment. You will see how that fits together later on. So we look at problems that may occur when isolating actions from different transactions. What are the possible problem scenarios? And when you deal with transactions, it really much feels something like that. Yeah? You fix one of the problems in controlling concurrent access, and then you feel like, yeah, nice. Yeah? So there's two other problems left, and actually by chopping off one of the heads of the dragon, two other heads grew as a result of that. Yeah? It's really wild. I mean, in particular, maybe that's a little bit too much for this lecture, but there's reasoning, for instance, that by how we address these problems, yeah, this tuple-based locking, for instance, you could argue that it actually triggers certain types of other problems. Yeah? So you have a solution, tuple-based locking, yeah? You chop off the head of the dragon, and as a result of that, two other heads will grow. Yeah? So just... yeah, you don't have to understand that at this point in time. I just tell you that's how it feels. This entire story of concurrency control. So it's tricky. So let's look at these three problems. Yeah? And there's fixed terminology for these problems, and one is a dirty read. So what is a dirty read? That refers to reading of a value by a transaction that was written by another uncommitted or aborted transaction. So in other words, one transaction is seeing what the other transaction is doing, even though that other transaction didn't commit yet. Yeah? So here you see that in that schedule. So you have two transactions, 1 and 2. So transaction 1 is writing data object A, then transaction 2 is reading data object A, and I'm assuming here in this schedule that whatever was written here, this is reading the same version that was written here by that transaction. And that is a dirty read, because transaction 2 reads something where I'm not sure about whether it will be committed anyway. Yeah, I have no idea at this point in time whether that transaction 1 will commit or not. I mean, you can look ahead and say, yeah, it will commit, so don't worry, Professor Dittrich, it's all fine. But again, think about this operation at a time mode we are in. Yeah? In an operation at a time mode, the database receives operations one by one. It doesn't know at that point in time whether the transaction commits. Versus if you receive all of this in a batch, well, then you're fine. That is easy. Yeah? You see all of the history, all of the schedule, then you know, yeah, this is actually not a dirty read because I know that this will commit. Yeah? So we're really arguing along the lines of, with the information I have once this, question? With this information I have once this stuff, once the operation gets executed. Yeah? So what can I say about that? And the only thing I can say is, yeah, that's a dirty read. The same, different thing is here. This is not a dirty read because this is referring to a change done by this transaction. B was written by transaction 2 and now is read by the same transaction again. This is not a dirty read. This is just the local view of that transaction. Yeah? A dirty read is only with respect to some other transaction, but not to the stuff I wrote in my transaction. But here again is a dirty read. Now transaction 1 is reading the stuff written by B. Yeah, so this would be a dirty read, obviously. Yeah, and we should avoid this stuff because it obviously breaks isolation. Isolation is saying, no, the changes by other transactions should not be visible. Yeah, that's problem 1. Problem 2 is a non-repeatable read. That means a transaction reads a value multiple times and reads it multiple times. When it reads the value once, it gets 42, and the second time it gets 43. So a different value is being read, even though it should, in theory, be the same thing. So here you see it in the schedule. So I'm reading object A, and I'm reading it again, and let's hope that I'm reading the same stuff here. So here actually in the schedule you see that A was not modified. So A must be the same value here. So you can conclude that, I mean, that's a repeatable read. So whatever I'm reading here must be the same as here. However, now consider that a transaction concurrently writes to A, and then you read A again in transaction 1, then A may have changed. Yeah? If A was changed to a different value by transaction 2, now all of a sudden, yeah, if you read 42 here and now you read 43 here, that's a non-repeatable read. Yeah? All of a sudden the world looks different, even though isolation assumes, no, I own the database. No one else is operating on the database. You see a different world. You see, hey, now it's 42, it was 43. Hey? Yeah, it's like a bug in the matrix. A little bit, yeah. So all of a sudden there are two cats walking along the aisle, yeah, one after another, and that, hey, well, what's happening? So there's someone else playing with the database. I was assuming I was alone playing with the database. Yeah? So that's the problem of a repeatable read, and we have to avoid that. Yeah, and related to that is what is called a cascading rollback. That problem always occurs when one transaction is reading stuff and then afterwards writing new values. And we don't know whether the new values might have been influenced by that old value. So here a simple example is the following. You write in transaction 1, you read in the same data object in transaction 2, and now transaction 2 writes something. It writes a B. And again, recall that we don't know what the application logic is. We have no idea. Yeah? So the problem is, was this new value of B influenced by that data value of A? If that is the case, B was influenced by that write operation on A. So we have a dependency from that write operation from transaction A to write operation 2 by the write operation on B of transaction 2. Yeah? So here's a dependency, a possible dependency. And now if transaction 1 says abort, should actually A1, right? Should be A1. Yeah, then this might have written a value that was influenced by a by a non-existing value, a value that shouldn't have been existed at any point. Yeah. So that's basically a transitional effect you're having through the database. Yeah. You're reading something from an unfinished transaction. Based on that, you write something. And now if that happens again from another transaction, you have a cascade of those operations. So that is illustrated here. Here you see the same thing just happening as a cascade of transactions. So here's the same thing. Transaction 1 writes something to object A. and it doesn't do anything. There's no commit happening. Eventually it will abort, but at this point in time we have no idea whether transaction 1 will commit or not. So transaction 2 reads that value and writes something to B. Now B, at this point in time, possibly contains information where we are not sure whether that will be persisted anyway in the database. Yeah? And so on. Now transaction 3 reads this B value and writes something to C. Now you want to commit. And the problem here is you are not allowed to commit at this point in time because you don't know whether what you wrote is based on consistent data in the database, on data that was written by committed transactions. So if this guy now says abort, all of these writes here have to be undone, have to be rolled back because they're invalid. Yeah? They potentially depend on this dirty write operation. Yeah? So, and that may trigger many aborts, many transactions that have to be undone and rolled back in the system. So it's not only a correctness problem, that may also lead to a performance problem in the database system. Yeah? Assume the situation that this stuff piles up. Assume transaction T1 is really long running, takes minutes and minutes, and thousands and 10,000s of transactions work in this mode, like transactions 2 and 3, and then you have thousands of transactions, and all of a sudden T1 says, no, I'm not in the mood to commit today. I don't care whether 10,000 other transactions have to be rolled back. That's not my problem, right? I mean, I have to make sure that I'm happy, that I can commit. Who cares about these other 10,000 transactions? Yeah? So it will abort. Yeah?
Am I getting something wrong? I thought that isolation prevents other T's to read something which was not committed.
Yes. Yeah, okay. No. Isolation means, so isolation, that's the isolation paradise. Yes, there's no conflicts like between humans. There's no conflicts between colleagues and humans. Everyone is happy, and there's no disputes and arguments. Yeah? And the same here. Yeah? That's the ideal world we want to go to. Yeah? And what I'm now illustrating is we're not there yet. We have to go there, but if you don't do anything, those are the problems that can occur. Yeah? So so I'm not in the problem space saying, obviously, if you concurrently run transactions, those are the kind of problem classes that may occur. Yeah? And now, the following we will look at, okay, how do we fix that? How do we avoid this stuff to get to like isolation heaven, isolation paradise? Yeah? Okay. Yeah, so how do we avoid cascading rollbacks? And one central idea that was done early on in databases, not sure whether it was even the 70s or the 80s, very old idea also in computer science, but this is a database variant of it that's called tuple-based locking. So based on a tuple in a relation, we will allow the database system to acquire logs and to release logs. And again, this is nothing you have to worry about. If you, for whatever reason, ever ended up reading the Postgres documentation, yeah, may happen. Yeah? It happens to the best of us. You will see there's locking, there's explicit locking that you can do with Postgres, and other database systems also allow you to do that. Don't do it. Don't do it. That's on a different level, and that might be relevant if you develop web applications. Maybe we talk about that next week. Not sure. But for the moment, you can completely ignore that. So I will be talking about, in the following, about stuff the database system is doing for you internally, automatically. You don't have to worry about all of this stuff. That's all implemented. I'm just explaining how it works internally. But you don't have to acquire logs manually. No, you don't have to do that in this class. Yeah? So how does that work? So what does the database system do? So we have tuple-based logs, and basically there are two kinds. One is a read log, and one is a write log. And the idea is that any operation that wants to read a tuple must first acquire a read log. Any operation that wants to change a tuple must first acquire a write log. And there are different names for that. So read log is also called a shared log, an R or an S log. And the write log is sometimes called exclusive log, or X for exclusive. So then the third point means if an operation doesn't receive a read or write log, the operation must wait until it is allocated, until it can acquire that log. Yeah? So now you can't just execute the operations anymore, but before executing the operation, you must ask the database system, hey, can you give me a read log for whatever, whatever? And if the database system says, yeah, here you have it, yeah, then you can go ahead with your operation. But if the database system says, no, you don't get that log, well, then you have to wait. Yeah? That's basically the mechanism here. And important is that all of these logs must be returned at the latest at the end of the transaction. Yeah? If you keep the log forever, no one else will be able to read or write to a specific tuple anymore. That's very important. If you don't follow for, you will screw up the algorithm. So some notation, we denote a read log of transaction Ti on data object aj with get rlog I on aj. aj being the data object and I again is an index of the transaction. And then you do the same, you can either write get rlog or get slog. And for the exclusive logs you write an x and then you have a release log to release a specific log on that data object you acquired before. Yeah, that's basically the idea of tuple-based logging. And then it's important that you follow a compatibility matrix. So here, the ruling is really easy. So, so when you want to acquire a log, yeah, the database system will check if no write log exists, any number of read logs are allowed, meaning multiple transactions can read the same tuple at the same time. That's all okay. No, yeah, as I said last time, many people reading the database or here tuple at the same time, that's not a problem. Everything is fine. Yeah? You're in trouble once one transaction starts writing stuff. Yeah? Then you have to be careful. But everybody just reading, yeah, that's fine. Yeah? If no read or write log exists, one write log is allowed. Meaning you want to acquire a log on a tuple for writing, and that is okay if no other read or write log was given out by the database system for that tuple. That's fine. Yeah? So that also means a write log is exclusive. There can only be one write log on a tuple, but not two. No way. Yeah? Not two. Yeah, whatever. So here's the metrics you have to follow. Yeah? So that's a requested log, a read log, a shared log, and an exclusive log. And that's what I just explained. Yeah? So if there's no logs existing, yeah, no logs, that means this, yeah, whatever log you request here, you will get it. If there's the existing logs is only read and you're requesting a read log, that's also fine. But if you request a write log and there's either a shared log, a read log, or a write log, exclusive log, then you don't get that log. Then that transaction has to wait processing. And again, recall that I told you the transaction defines an order of its operations. So if the transaction is at operation 42 and it can't acquire the log, it has to wait. It's not allowed to jump over that. Yeah? It has to wait for the database to give it the log for that operation 42. So that's log compatibility. Yeah, and then we have to differentiate between short-term logs and long-term logs. So what is a short-term log? That is written here that, maybe the example, maybe let's look at the example, it's much easier to understand. Short-term meaning immediately before the operation, you try to acquire the log, and once you're done reading, you give it back. Yeah, here you want to read data object A. Yeah, okay, so you immediately, you get the log, yeah? If you get the log, it's fine, you're allowed to read the data object, and then you immediately release the log afterwards. Or for write, the same thing. Here, you want to write to data object A, so you get the exclusive log, and if you get it, you will proceed to writing that data item A. If you don't get the X log here, the transaction will wait. But anyway, immediately after having written that data object, you will release the log. In other words, you give the log back to the database system. Yeah? That is what's called a short-term log. And the long-term log is a different story. And here you have different modes in which you can run the database. And the most prominent is called two-phase logging. Yeah, and that is what is used in database systems widely. Two-phase logging comes in different flavors. We will get to that. But the most basic way, the easiest way of using two-phase locking is this one on this slide. So the main idea is the following. Basically, you have two phases, the growth phase and the shrinking phase. So you say, okay, here on the, let's go a little bit up. So here there's time, yeah? So the transaction is running. It starts with begin and ends with commit. So, and in that time, it is allowed to acquire locks. Ask the database system, hey, I want to have a lock on that, I want to have a lock on that. It said, okay, yes, no, whatever. Yeah? And you see two phases. Actually, you could also argue it's three. But basically, there's a growth phase. That is where the transaction acquires locks. And then there's a shrinking phase. That is where the transaction gives those locks back to the database system. And any transaction following this principle that there's a growth phase, and then there's a shrinking phase, and not a growth phase, then shrinking, and then grows again, and shrinking, and grows, and shrink, and grows, something like that. That's not 2PL. So 2PL is really one phase where it's growing, and the other where it's shrinking. And potentially, of course, there's a plateau here. I mean, you could have those plateaus in the middle as well. Yeah? Important is there's no interleaving of growing and shrinking. Then it's two-phase locking. And the interesting thing is then that this 2PL only allows schedules that are conflict serializable. Again, recall what we had last time. Hey, conflict serializable, that was the cool stuff. That was meaning, hey, that's equivalent to a serial schedule. So, come on. So we're 10 to 11 today. We can go to Mensa. Mensa is closed. And it doesn't matter because we can't go to Mensa because there are many things that are still unresolved. Yeah, but it sounds like, hey, it's conflict serializable. That's really, I mean, what else needs to be done? Right? No, we did everything. Did we? No, unfortunately not. Yeah. Also, watch out for the counter of the slides. So that's the bad news here. We had slide 14 of 49. And I'm leaving many things away here. Yeah? Just a very high-level story. Yeah? So the problem is schedules that contain aborted transactions. Yeah? In other words, transactions can be aborted at any time by the user or database system. So conflict serializability only means that the schedule is equivalent to a serial schedule, but not that the transactions aborted in this schedule take back their introduced changes. So what I'm showing with conflict serializability is only, I have a bunch of transactions, some of them commit, some of them abort, and after interleaving them in a way that I can show that the schedule is conflict serializable, the state of the database system will be equivalent to one of the serial schedules of the transactions. Yeah, that's what I'm showing with conflict serializability. So I'm saying, yeah, what you did with your interleaving is equivalent to some serial execution. But hey, what is the idea of isolation? What is the idea of atomicity? The idea of atomicity is that you commit all or nothing, and if you say abort, it should be nothing. Yeah, but now we're talking about a schedule where you committed something. Yeah, you made something durable that's also violated. You made something durable that should not become durable because, hey, you didn't commit the transaction. So you have changes in your database that were done by aborted transaction. Still, your conflict serializable. Well, Houston, you have a problem. So that problem was not solved. Two-phase locking does not solve that problem. So there's a longer story for that. And then there are different ways to avoid that. And one is a stricter version of two-phase locking. Yeah? So strict 2PL or S2PL means now we only have a growth phase. There's no shrinking phase anymore. Yeah? So the graph looks like this. So the shrinking phase is gone. And the idea is while I'm running the transaction, yeah, as we had seen that before, I was already releasing some of those locks. I'm not doing that anymore. When I acquire a lock, I keep the lock until I commit or until I abort, but not before, not while running. Yeah, that is the idea of two-phase locking. And then the interesting thing is that this thing avoids cascading rollbacks. Why does it avoid cascading rollbacks? Do you have a slide for that? Maybe I can show it here. Let's look a little bit back at cascading rollbacks. So does anyone see it? Why it would avoid cascading rollbacks under strict 2PL? Yeah? Mm-hmm.
And then this could mess up the execution of my transaction.
Right, but now we are in strict 2PL, so why can't that happen anymore?
Because now I'm not freeing the log until my current
Yes. Exactly. Yeah, so that's what you're seeing here. So before we had these short-term locks and potential. Yeah, what do you want to say?
But shouldn't you make it, put that in your locking scheme that such a thing couldn't happen? Why would you do that outside of how your logs work? It feels like your logs should take care that such cascading rollbacks.
No, the locks don't take care. That's actually the locking scheme implemented by concurrency control of the database system. It will make sure that these things don't happen. And that's why we will be using strict 2PL rather than the standard 2PL. Yeah, so the contract I'm following will be transactions are not allowed to give back logs before committing or aborting. Yeah, and that's basically what you had in mind, right? Yeah, and here for the problem, here for this example, you see that the problem only occurred because here transaction 2 was able to read data object A. And if you think about the compatibility metrics, if now transaction 1 keeps the lock on data object A until aborting, T2 has to acquire a read log at that point in time, and then the database system will say, no, you don't get that because someone is still writing on that stuff, or someone else has the write log, so you're not allowed to read it. Yeah? So the problem won't occur. And of course, iteratively here it also can't occur. I mean, read B. Okay, so you see here this schedule will be reordered. Yeah? You will see now if transaction 3 reads B, here it will read something that wasn't written at that point in time. Yeah? So transaction 2 will stop, then T3 will send the read B operation. There is no log existing because this wasn't written yet. Yeah? So T3 will execute before T2 and stuff like that. Yeah? These things will happen. So the database system will reorder how these actions are being executed. Okay, so strict 2PL avoids cascading rollbacks. Right. Yeah. So all of these things are solved with strict 2PL. They're off the table. But there's still other problems that can occur. And one has this fancy name phantom problem. And then we will also be looking at the deadlock problem. So what is a phantom problem? This is, I would say, wild terminology. Because in spirit, it's the same problem as repeatable read. Phantom problem is just, I mean, the difference here, I'll try to phrase it here. So repeatable read is, you read a single data object, yeah, and we defined it, oh, that's at most one tuple, or a couple of attributes by one tuple, identified by its ID, by its primary key. And then you read it once, you get one value, you read it a second time, you get another value. Oh, that's a non-repeatable read. Phantom problem is on the level where you're not arguing along single tuples, but a bunch of tuples that are typically selected by some where condition, not on the primary key. So you don't have a condition ID equals 42, but you have a condition like first name equals Jens, or whatever, student age equals 23 or something like that. So multiple tuples get selected. And that is what the phantom problem is about. So maybe I show you the example and then you can ponder about that in the break a little bit. So that's a phantom problem. So here we have something selecting the sum of all accounts, the sum of the balance over all accounts. So what's the money that's in the bank? Yeah, and that returns a certain value X. That is what one transaction is doing. Now concurrently, T2 is inserting a new account. So a client has opened an account with the bank, so you have to insert a new tuple with a non-existing account number 42 and the initial balance of that account. So here you're adding a tuple to the database. What I explained to you before is, yeah, we have logs on tuples, right? So as long as we log the tuples, everything is fine. Well, but now I'm inserting a tuple that didn't exist before, so by definition it wasn't logged. Yeah? Now, in transaction 1, I run the same query again, yeah, including the new tuple, and now I get a higher value. I get x plus 5,000, and that's kind of a repeatable read, however, on a multiple tuple level. Yeah, so that is triggered due to a new tuple being inserted. So, and that is a name. That's a phantom. Huh? You look there, and there's just no one there. You look at, didn't I see it? Oh, there was a tuple, wasn't there a tuple, right? And then maybe you look again, and the tuple is gone, right? Because it might be that afterwards the bank deletes the account. Yeah, imagine the situation where afterwards here's a delete happening. Yeah, delete. Whatever. Maybe. Here you do delete with the same account, yeah, and then you're back to the same balance here, yeah. So that is how the terminology was phrased. You look and there's nothing there, and then you look again, oh, there's someone there. You look, it's again gone. Was it just my imagination? That's what's called a phantom tuple, and important to understand is sometimes in textbooks you see, you always see these examples with inserts. These problems may also occur when a tuple gets changed or deleted. Yeah, we will. I think I have another example later on in the lecture. Yeah? But the most basic problem of a phantom problem is something like that. You insert something concurrently, you have a select in a concurrent transaction, all of a sudden you got a different value, which obviously violates isolation because you should always be seeing the same result within the transaction, no matter what happens with other transactions. So that's violating isolation, and that is not fixed with what we learned so far. So phantom problem occurring because we're selecting multiple tuples here. Yeah? In this case, the entire relations, the entire accounts relations, all the tuples from that relation. And here's a more detailed explanation with a more like a mathematical notation. So basically, you read multiple tuples, yeah, and what we learned before, for all of these tuples in the accounts relations, for all of these T element accounts, you do a read operation on their balance. That's what you're doing here, and that's what you're doing here again. However, what you're doing concurrently is you're adding a new tuple to the set of tuples represented by the accounts relation. And that's a problem. So locking single tuples doesn't fix that problem. Yeah? And as said before, you can also do that without an insert or delete. So here's a situation where the phantom problem occurs due to a where clause. So here selecting only the sum of those accounts that have a balance that is strictly greater than 900. So that's a change to the previous example, same statement executed here again. And now you don't insert an account, but you set the balance of one of the accounts to something higher than 900. Yeah, that's what's happening here. And now all of a sudden you don't have two tuples anymore that qualify, but three tuples. So it's the same thing. You're reading something that differs from what you read before. That's again the phantom problem due to selecting multiple tuples in the where clause. Yeah? And that's also a phantom problem, even though you don't do an insert here. And how that is fixed is through predicate locking. So not locking a single tuple anymore. Now we're going beyond that and say, okay, to avoid this kind of stuff, we have to lock entire ranges of domains in the database. So actually, when we have a query like that, maybe we start here, we have to make sure that no one messes around with data where the balance is greater than 900. That is what happened before in that example. Here you saw, okay, someone changed a tuple to have a balance greater than 900. And now what we are doing with predicate locking is no one is allowed to change values such that their balance will be greater than 900. That is what predicate locking is about. So basically this condition that's being used here will be used as a lock. Yeah? I'm not locking a single value, I'm locking a single tuple, I'm locking an entire range. Yeah? Whatever happens in that range, in that balance greater than 900 range, be it that someone wants to delete a tuple with such a balance, that someone wants to insert a tuple with that balance, or someone wants to change an existing tuple to be added to that range or be removed from that range. That will be avoided by predicate lock, by locking the entire range of values in that condition. And if you don't have a where clause, well, something like that, we had that before without a where clause, actually that means where true. Yeah? That's the same query. Basically, that means that you lock the entire relation under predicate locking. Yeah, and predicate locking only works under certain conditions. That's basically what this slide is saying. I start with the example. So basically the problem is predicate locks are fine if they are with respect to the same attribute of that relation. However, if you have a lock, that's what this example is about actually. If you want to have a predicate lock here on this value, and then you have another predicate lock on the y attribute, so this is x and that is y, they're not compatible with each other because you don't know what for the specific tuples what the x values and their y tuples are. So typically predicate locking makes a lot of sense if you have queries that that are specified against the same attribute. Then you can do reasoning. Yeah, then you can say, okay, you're in that range, you're in this range, you're in that. That's okay. That's all disjoint. Everything is fine. Oh, someone wants to enter on the same range, on that same attribute. Yeah, you can't do that. Please wait until this guy is finished. That's all fine. Then predicate locking works. But as soon a query selects with respect to a different attribute, then this won't help you anymore. Yeah? So you have to lock everything basically. Yeah, but that's a remedy to fix these phantom problems. Predicate locking. So there's one problem left, and that is a deadlock problem. So deadlock meaning you have two transactions, T1 and T2, and they block each other. So transaction 1 wants to write to data object A, transaction 2 wants to write data object B. Yeah, it's all fine. They get those respective exclusive locks. Yeah. Then transaction 1 wants to write to data object B as well. It has to wait at this point in time because the lock is not available. Transaction 1 has to wait processing, but T2 is allowed to continue. It now wants to write on data object A. It has to wait because the lock was already given out to transaction 1. So that's a classical deadlock. Yeah? The transactions are waiting for each other. Nothing is happening anymore. The database is stalled. Nothing happens anymore. And that you want to avoid, of course, as well, because it will stop your database from processing transactions. So how do we do this? One thing to do that would be to even make a two-phase locking, make a strict two-phase locking even stricter, and that's then called conservative two-phase locking. The idea is that you don't have a growth phase anymore. Yeah, so you have, when the transaction begins processing, you say, okay, you must tell me in advance which locks you want to have. Yeah? So that's basically, here's the database, here's a transaction. Yeah? So transaction, give me that lock, I want to have that lock and that lock. Yeah? And then the database system, here are the locks, now you go on. Yeah? And then the transaction is, oh shit, I forgot, I also want to have that lock. And then the database system, no, we are really conservative. You're not allowed to continue, I will roll you back. Yeah? It's like in a restaurant. Yeah? So basically you sit in a restaurant and the waiter comes and you have to make crystal clear what you want to eat. Yeah? And I want to eat this and then this dish and that dish and afterwards. Yeah? And I want to drink this and in an hour I want to drink another beer and 2 hours later I want to drink another beer. Yeah? And that wouldn't work in this world because typically restaurant is like, hey, okay, now I had my lunch, I had my dinner, but I want to have another drink, I want to have another water and stuff like that. That doesn't work under conservative two-phase locking. Yeah? You have to order your stuff at the beginning. Actually, when entering the restaurant, before taking a seat at the table, ironically, you have to say that's what I want to eat and that's what I want to drink. Yeah? And so that's completely unrealistic. Yeah? It would prevent deadlocks, but it's unrealistic. So here's an overview of the different 2PL variants that I personally find super helpful because here you see where we started. Yeah? So that's how we started. That's a standard two-phase locking. And this space is a dirty read space. Yeah? One transaction releasing locks, the other transaction releasing locks before committing. Yeah? That is the stuff that allows for dirty reads from other transactions. Yeah? Because now all of a sudden the locks are available. Another transaction comes in and says, yeah, I'm reading this stuff. I don't care whether you committed. I mean, who cares, right? Yeah? And then you have these dirty read problem, non-repeatable read stuff, and the cascading rollback problems. And this space here is a deadlock space. Yeah? That's basically what we still had in the strict 2PL. Deadlock meaning, as in this example, so maybe go back to the example, I think that explains it very well. Yeah? As in this example, so here it doesn't work like T1 says, yeah, I want to get an X lock on A and B. Yeah, and only then I will continue processing. Yeah, that would be conservative. Huh? That's not happening. It's requiring one lock. This is requiring one lock. It's requiring acquiring another lock and acquiring another lock. So it's still strict 2PL rather than conservative 2PL. And that's why there is a deadlock here. Yeah? So you would fix that if T1 said, I want to get an X lock on A and B. Yeah, then T1 will process all of that, and then it will release the locks on A and B, and then T2 will continue processing, requiring the locks, and so forth and so forth. Yeah. That is what conservative or pre-claiming, as it is called, is doing. Yeah? So in theory, that's a good idea. In practice, it doesn't work, and this is why it doesn't work. So what happens in transactions is that when starting the transaction, the transaction doesn't know which are the tuples affected in the operation of the transaction. Yeah? So here, for instance, which tuples are to be read depends on the condition in the application code. Here, the value of x, whatever x is. So maybe there was another read operation happening here. So here you're saying, okay, if it's strictly greater, you select this tuple with a 43. If it's smaller equal, then you select 42. Yeah? So depending on what you do here, you might need to acquire a lock on this tuple, or you might need to acquire a lock on that tuple. I mean, of course, you could be super conservative, analyze the transaction, and just lock every possible path, everything that may occur. Yeah? But then you lock large portions of the database for nothing. Yeah? Even though you never touch the stuff. Yeah? So it's really an unrealistic thing, and it doesn't work for all transactions. What you do instead is called a wait-for graph. So a wait-for graph consists of the set of running transactions, so one vertice for each transaction, as well as a set of directed edges. That is a directed edge from Ti to Tj if Ti waits for a lock held by Tj. Well, and then if you remember what we talked about in part 1, well, yeah, it's the same thing. There's this conflict graph on the transaction level. It's the same thing we're now implementing in the database system. Yeah, that's another cool part in concurrency control. So when you look at textbook concurrency control, there's always reasoning like, yeah, you do this ordering, tra-la-la-la-la-la, and then typically the professor says, yeah, no, but we forget all about that, and now we do a real algorithm. Forget about theory, we proved that once, and now it's algorithms. Yeah? And the cool thing is that very often in concurrency control you see that there's a theoretical concept and you can implement it directly for your algorithm, yeah? And then everything is fixed. Yeah? And that's very neat here, and that's exactly what's happening here. Yeah? Because what you need to do in a database is you don't want to have cycles. Yeah? A cycle in the wait for graph, yeah? Because that is indicating a deadlock. And I have a couple of examples for that. So if a cycle exists in the wait for graph, vertices must be removed until there is no cycle left. So the graph is cycle free. And removing vertices means the corresponding transactions, the application program the transaction that wants to compute has to be removed, it has to be aborted, has to be rolled back. So this is not the user sending an abort or rollback. This is the database system understanding, oh yeah, you two guys, you're waiting for each other. that's not going to work. I will shoot down one of you. And then the other can compute, and the other, yeah, you can submit again. You can try again and send the transaction again. Yeah, so it's a database system aborting a transaction to avoid, to get rid of a deadlock problem. Yeah. Here's an example. So we have a graph with a cycle. Yeah, you have 3 transactions. And here's a cycle, obviously, and a couple of other cycles. Here you could also see the cycle. Here's a cycle. Here's a cycle. That's a cycle. Here's a cycle, and so forth and so forth. Yeah? And what you could do is you remove transaction 2. So if you abort transaction 2, yeah, like done here, yeah, all of the edges go away, all of these dependencies go away, and you end up with something like that. So T1 is waiting for T3, yeah, but there's no cycle. That's okay, no deadlock, everything is fine. So in this world, T1 and T3 will be executed, and T2 can send a request to the database system again, everything is fine. Okay. So in the database world, there are, so I'm starting to summarize in the following, summarize what we learned, because that's already the major techniques you need to know to understand how concurrency control works. But I'm now again trying to contrast and clarify this confusing terminology you end up running into in the database world. Yeah? And one is conflict serializable and serializable here in Courier font, meaning, so that's sometimes confusing. If people say it's serializable, what do they mean? Serializable is not the same thing as conflict serializable. Conflict serializable is what we learned about this. Yeah, the conflict operations are in the same order as some serial schedule. That's conflict serializable. Serializable, so this right, serializable actually means, no, this is isolation heaven. This is the isolation paradise. No problems may occur with respect to isolation. Yeah, and that is what's meant by serializable in Courier font. Yeah? People sometimes don't use Courier font, so it's confusing. So you better ask back what's meant. Yeah, if there's a confusion about that. Yeah? What you want to have is this one, serializable. Yeah? Meaning you don't have any of those problems we talked about in isolation. So if you only have conflict serializable, we have the problems, what if not all the transactions in the schedule commit? Yeah? So there are transactions that write stuff to the database, and then they do an abort, so there's stuff on the database from uncommitted transactions that's not allowed, that shouldn't happen. No? Or this phantom problem that occurs to operations reading or writing more than one tuple, and then you see a phantom, and you don't see a phantom. Yeah? That's not solved by conflict serializable. Yeah? And that's why we did more. So we achieve perfect isolation by doing these other things, yeah, by doing predicate locking and by doing strict 2PL, and that will avoid these kind of problems. Yeah. That's what serializable means, perfect isolation. Yeah, and that's the same what I just said. I made 2 slides about that. We're repeating it over and over again, saying that's not the same thing. It's really confusing. Also in textbooks, sometimes I find it really confusing when I read that. Says, well, what is he talking about currently? Or she? Is it which serializable? Yeah, so serializable means perfect isolation. That's what we want to have. Yeah, and now to mess up things a little bit more, now we have an idea what isolation means. So there's one thing you have to know, because it unfortunately still exists in database systems, and that is called isolation levels. So what happened once people got that right, I don't know, in the 80s or I think it was solved in the 80s, very early, a long time ago, database people solved isolation. And, but then they found out, ooh, my database is pretty slow now, right? I'm doing all of this concurrency control, all of these log acquiring, back and forth. I've completely ruined performance. That's not what I want to have. I paid so much money for the license of my database system, but now it's completely ruining the performance of my application. So at the time, people introduced a knob in the database system. Here, a knob like that, where you can say, okay, how much isolation do you want in my database system? Yeah? So you could do a trade all of a sudden. You could say, I want to have a little less isolation. I'm completely fine with phantom problems and deadlocks and even repeatable reads. Who cares about that? Yeah, as long as the performance goes up. Yeah, and so that's an expert's knob. That's really yeah, you really want to understand when you touch this stuff whether that's a good idea. Yeah, the problem, and that's the reason why I'm explaining that. So you would expect, if you install a database system, that the knob is set to perfect isolation, to isolation heaven, and that is not the case. Yeah? Most database systems ship with this lever being set to not to maximum volume, maximum isolation, but somewhere in the middle. And that can be pretty surprising, yeah? Because hey, I learned about there's perfect isolation. There's no need to worry about isolation anymore because the database system will fix it. Yeah, but then the database vendor decided, no, we don't want to look that bad in performance, and who cares about correctness? So we set the lever in the middle. Yeah, so you have to be really careful. And the first thing you do when you install a database system is to look up, hey, what is the isolation level set to? Yeah? And I want to explain that a little bit, what the effects are and how that maps to what we learned so far. So here's a trade, here's a deal. Yeah? You gain higher performance, but you have weaker isolation guarantees, and then it depends on your application. Yeah? So the idea was really, the application developers fully understand what the database system is doing and which kind of problems occur, and then the database administrator can set the knob and everything is fine. Yeah? That's really a good joke, yeah? Because I mean, just this year there was a paper at the database conference explaining that application developers don't understand that. Yeah? And so basically what they did in that paper was pretty cool actually. They crawled GitHub repositories and error messages for possible isolation anomalies, isolation problems. And they found out that there were many of those problems due to the isolation level not set to serializable. And the developers didn't understand that. They didn't understand that the problem could have been fixed in the first place by just setting isolation to serializable. Job done. Yeah? But then they had, why do we have that? Why is there a conflict here anyway? Blah, 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 blah. Yeah? So it's really important to understand this stuff. Yeah, okay, so that's what I said. Default is typically not something like that. Perfect isolation should be implemented by every database system. That's another expectation, as you will see that in a moment. So you get one of the most expensive database systems in the world. You set it to serializable and you assume it's isolation heaven. Yeah, and there's at least one system that says, no, it's not. It's called serializable, you know, right? But no, it's not. Yeah, so I'll show the example in a moment. If in doubt, that's the most important thing. Yeah? Read the documentation. Yeah? Read the documentation about the database system you're using. What is this system doing with isolation levels? Yeah, and this is one way how you can do this deal. Yeah? So here we have the different isolation levels. So that's perfect isolation. So we have all the bells and whistles, 2PL with predicate logs. And then you can set a transaction to a weaker isolation level. Yeah? Let's start from the beginning. You can say read uncommitted. Yeah? Read uncommitted data, meaning when you want to do a read operation, you don't even acquire a log anymore. You just read without waiting for a log. Yeah? You just read. Yeah? And that's actually, that's okay. In databases, if you want to do fast browsing of data and you know it doesn't matter whether it's super correct what I'm reading, I'm just browsing this stuff. It's like browsing the web, then maybe that's a good thing. Yeah? But still have all of these problems. So here you see the write operations are always with respect to strict 2PL. Yeah? So that's unchanged. Yeah? Whatever your isolation level, it's always strict 2PL. Yeah? But what I'm changing is the read logs. Yeah? So here with read committed, I'm saying, okay, in the read committed isolation level, okay, I will use short-term logs. Yeah? What we had before, immediately before the read operation, you acquire the read log, immediately afterwards you give it back. Yeah? If you do something like that, you avoid dirty read and cascading rollback. However, you still have a non-repeatable read. In repeatable read isolation level, you use strict 2PL on both read and write operations. Yeah? Again, this is only with respect to single tuples. Therefore, there are phantoms which occur due to selecting multiple tuples with a where clause. Yeah? If you want to have the perfect isolation, you have to additionally introduce predicate locks, and then you have none of these problems. Yeah? So those are typical isolation levels. And to make it more complex, you will see that different database systems will offer different the isolation levels may have the same names, but may avoid a different set of problems. In particular, when you want to read about Postgres, you will see that this looks completely different. And the reason for that being that Postgres uses a different concurrency control algorithm. So you have to be careful. Bottom line, takeaway message is always set it to serializable. So all of this deal was introduced when databases were really slow. Were operating on super big hard disks. Access times were crazily slow, and there were really performance problems. These days, in 99% of the situations, you won't have those problems. So there's no reason to use any of those isolation levels, actually. Set it to serializable, and don't touch any of the other isolation levels. So here's an example how you do that. So you do it for a transaction. That's a Postgres SQL syntax, how that is done. Begin transaction. And then you set the isolation level here to one of those four. But the syntax may depend on the system, of course. And in Postgres, it's read committed. So read committed, the second highest, not the second highest, the second lowest. So you're only so reading committed data. That is the default in Postgres. So you want to change that probably depending on your application. So here again, I explained what we learned so far as extremes. The two extremes we were looking at. So one extreme is something like read uncommitted. You could even make it more extreme by also discarding the write logs. But here, in read uncommitted, that means there's no read logs whatsoever. So you do not lock data objects and predicates, and any number of problems with asset and deadlocks may occur. That's a bad thing. But the good thing is other transactions never have to wait for reading, and you get excellent performance. Versus you have a very restrictive protocol to lock objects and predicates. So you make sure that makes sure that there's no problems with asset and deadlocks. However, often other transactions have to wait, and they may have to wait unnecessarily. So you typically, what happens is that you block out transactions, you stop transactions because you believe they might trigger a problem. In fact, they wouldn't trigger a problem, but the database system doesn't understand that. So that's one effect, and the other is, of course, all the overhead for running this stuff. There's some overhead in the database system ruining performance. But that's basically the two extremes, and you can make a decision with this lever. I depicted here this volume lever, where you want to be in your application. I think we should look at that notebook a little bit, because you will use that in your assignments this week. So that's a little transaction manager we wrote a couple of years ago. One of my PhD students wrote that. Oops, what's going on? Do you see that? You see that? And basically, what you can do with that, I skip. So you can submit a schedule. So you can basically write, that's the schedule I want to submit to the database. And the syntax is, okay, it's the transaction and the number. Transaction 2 sends a begin. Transaction 2 wants to read something from that accounts table, row ID being 0. So row ID is some, read it as that's a key of that relation. So basically, I'm specifying a schedule here in linear order. And once you can do that, you can submit that schedule using a certain isolation level, as specified here, to the transaction manager. It's important that you keep this to false, because if you set it to true, it would be using a different concurrency control algorithm. That's part of the core lecture, but not part of this lecture. So that has to be set to false. And then basically this transaction manager can visualize this precedence graph, this waits for graph, and it can execute the schedule. And then you see, okay, that's the schedule being submitted, and that is that's on top of here, and that is the executed schedule. So here, due to this waiting, the transaction manager aborted some of the transactions and only sent some of those only executed some of those transactions. That's basically what this notebook allows you to do. Yeah? And in this, in the assignment of this week, you should use this and play with schedules and reason about, okay, why is that schedule like this? What will happen? What is the order going to be with the schedule and stuff like that? Huh? So this is basically simulating what we learned today, how the concurrency control works with 2PL and all of these things. Yeah? Okay. So to wrap up, what are the data management and analysis issues behind that? So how do we allow concurrent modification of data without creating erroneous data? Concurrency control. How do we design this so that the process and the resulting overall system is efficient? Yeah, using 2PL, for instance, with predicate locks or weakened guarantees by means of isolation levels. Modern database systems use MVCC in one of its zillion variants, or the combination with strict two-phase locking. That's part of the core lecture. Yeah? And now we transfer that a little bit back again to the concrete application. We started out with drawing money. Why is that slide in? Oh, didn't I comment it out? Interesting. Hey, I'm on the wrong version here. Sorry. I think we can skip over that slide. I wanted to remove that slide. So now we're withdrawing money with the read committed isolation level. Yeah? So transaction 1 gets the shared lock, the read lock on this data object it wants to read. And that's what we're seeing here. Is it zooming in for you as well? It's zooming in for you as well. Okay. So here we get a short-term read lock. Yeah? We get the lock, we read the data object, and then we release it again immediately. That's what read committed is about. Same happens here. Then we have this decision, okay, if that is greater 100, saying if there's enough money on that account, so I want to withdraw $100, yeah, and here the rule is basically, yeah, if you have the $100 on your account, you're allowed to actually withdraw it. If not, you have to abort. Yeah? That's basically the contract that this bank is doing with its customer. Yeah? So if you have that money, yeah, you get that lock, you get the right lock, write it, but you don't release it immediately afterwards. This is a long-term lock. This is strict 2PL, so releasing it with a commit at the same point in time. In contrast to the read locks, short-term locks here. Yeah? The same happens here in transaction 2. Here you see, again, you check whether there's enough money. Yeah, then you get the right lock, you write the new balance to the account, and so forth and so forth. Yeah? And now when you reason about that, you will see so here's a consistency condition, yeah, what I said, 100 euros about. So here T2 must wait for T1. T2 must wait for T1 at that point in time, only here. Yeah? Why does it have to wait? Because the X lock on K2 is only released here. So you have to wait at this point in time. Yeah? Actually, it is this point in time. You already did the check. So while so you read the stuff, the condition is fulfilled, you are allowed to remove $100. That is what happens here. Yeah? You wait for this X lock on K2, you get it, and then you continue, then T2 gets the X lock and writes the new balance to the account. Depending on what you read before. Yeah? So it read the account, the old account, before it was written to afterwards. You're seeing that? Yeah, so you read the old account here, and now it's writing the old account with respect to T2 to the database again. And that's a classical lost update, yeah, because you lost the stuff that was written here. Yeah? So the $100 that were deducted in transaction 1 were written to the database at that point in time, but now you're overriding it again with your worldview, which happens to be the same value here. But of course, what you did is you withdraw 100 euros in transaction 1, 100 euros in transaction 2, but the new value of the account is minus 100. Whatever you had before minus 100, yeah? You got 200 for 100. Yeah? So that's a good deal from the point of view of the customer. Yeah? So well, what should have happened is something like that. Yeah? So here you see it. Yeah? Before there was $100, so everything is fine. Yeah? And now afterwards there's $0 on that account. But the ATM returned $200 actually, yeah? But only billed $100 to the account. So what should have happened is something like that. So recall, we must be equivalent, database state must be equivalent to one of the serial orders. So if you execute T1 first and then T2, the account would have been 0, yeah? As well, however, T1 would have returned $100 and T2 would have aborted. Why would have T2 be aborted? Because T2 then would have read the new value of K2 that was just written by T1. So here you would have read 0. Then this condition would fail and the transaction 2 would abort. Do you see that? Yeah, so that's the serial order. And the same would happen the other way around here, of course. Yeah. First T2, everything's fine, $100 returned. Then T2, no, abort, because I don't have enough money on that account. Yeah. You see isolation level, read committed would ruin that. What happens if you do the same with repeatable read? So that's this slide. So what's the difference here? T2 must wait for T1. Yeah, one of the T2 must wait for T1. Here T1 must wait for T2. Why? Because I want to have the exclusive log on K2. However, now the change we are doing in repeatable read is we don't have short-term read logs anymore. We have long-term read logs. That's the only change I'm doing to the previous slide. Yeah? So here I returned the read log in read committed. I'm not doing that anymore here. I'm keeping the log I require here until the end of the transaction. Which means if I want to acquire a write log here, I have to wait because here this is blocking. Yeah? The same happens here. I want to acquire that write log. That's impossible because there is another read log that was issued here. Yeah? So here I get a read log here for T1, another read log for T2. Here I get a write log. That's impossible, because this is blocking. Here, get a write log. That's impossible because this is blocking. And just as a footnote, if one transaction has a read log, and now wants to have the write log on the same object, that's typically possible. Then you're escalating the log. Yeah? That's okay. The problem here occurs because someone else has a read log as well on the same data object. That's why we have a problem here. Yeah? But if it were just one transaction, like something like that, yeah, and then you first get the read log and then you say, no, I actually want to write, yeah, that would typically be fine. Yeah? Just escalate it. Yeah? That's okay. Strom sparen. 10% for 15 minutes. Let's hope for the best. Okay. Creating a new account with repeatable read. So that will obviously go into the phantom problem space. So here we select an average interest rate for everyone, for all accounts where the zip is equal to Saarbrücken. Then we insert a new account, and after the insert, actually that x value would have been 2. But we still use the old value of 1.5, do an update on everybody, including this one. Here we have a conflict. Yeah? So you again can reason along the state of before and after. So before, the state of the table is that. Afterwards, you change the interest rate of all of these 6, 6, 1, 2, 3 zips, tuples to 1.5. However, if you execute that in serial order, T1, first T1, then T2, then that would have been the result. If you executed T2, then T2, T1, this would have been the result. And none of that is equivalent to what you did in the interleaving. Yeah? So that's obviously an isolation problem. So let's switch to serializable. So switch to predicate locks. If you do predicate locks, yeah, this wouldn't have happened. Why wouldn't that have happened? So if you go to serializable, why would we avoid this problem? Yeah? Yes, the insert would have been prevented because in the where clause here, yeah, that would acquire a predicate lock. So everything will zip equals 66123. Yeah, and now this means when you do an insert, you have to check whether the tuple you want to insert violates any of those predicate locks. And that is the case. And that would violate the predicate lock. So that would mean here you have to wait. T1 completes processing, yeah, returns its locks, and then T2 continues processing. So that means that would have been equivalent to T1 first and then T2. That's what you get under serializable isolation level. Yeah? Right. Okay. So now, as promised, so we were in university. So we are in university here. Let's go back into reality. I promised you there's one very expensive database system that has an isolation level serializable, which is not perfect isolation. Just how does it look like? So here's a scenario. What you're seeing is you have two read operations. One is reading K2, the other K7. The same happens in a concurrent transaction. And the idea of that is a customer having two accounts, and the customer is allowed to withdraw money as long as the sum over both accounts is greater equal the amount of money you want to withdraw. Yeah, that's what's happening here. Yeah? So you want to withdraw 100 euros. Yeah, you see it here. And as long as you have the money, as the sum of the money on your accounts is greater than that, you're fine. You can run that transaction. The same happens here. It's basically the same transaction code, now interleaved. Yeah? These two transactions are run at the same time. And when you execute that, you basically see that before, in this situation, yeah, you have exactly 100 euros on your two accounts. Yeah? Assume that this is the accounts 2 and 7, as we said, so the sum is 100. And afterwards, you have minus 100 euros if you execute that. Whereas it should be like that. Again, you successfully execute T1, and then you abort T2, or if you do it the other way around, first T2 is executed successfully and T1 is aborted. So that would be consistent. Huh? And if you look at the isolation levels and then go again through it, well, with read committed, if the read locks are only held for a short time, write locks can be issued that allow to change both accounts. Yeah? So yeah, that would be a problem. Yeah? If you go for repeatable read, no, it wouldn't happen because the read locks then again, as in the example we had before, are held till the end, till commit. So other transactions won't get the write locks. Concurrent writing becomes impossible for transaction 2. However, we have a deadlock. Yeah? The deadlock would be created there. And then, as in the other example, serializable should fix that problem. Yeah? So if you set the isolation level to serializable, we have predicate logs and everything is fine anyway. Yeah? That's what we learned in this lecture. Yeah, except you're using Oracle. Oracle actually is one of the most prominent database systems in the world. Yes, like company-wise, on the same level as I think in value like SAP. They have a very famous product that is super expensive, but also has tons of features. And the Oracle allows for this problem. The schedule I showed you before, will run through and may create an inconsistent database state that violates isolation. And this problem is called write skew. And the problem was detected relatively late, I don't know, 15 years ago or something like that. And then many products fixed that, including Postgres and Microsoft SQL Server. The problem only occurs with certain classes of concurrency control algorithms, MBCC, as mentioned before, core lecture. And the basic problem here is that both transactions work on the same version of the database, the same snapshot, and then change different accounts. And yeah, so that's an example of a product that allows for something like that. So if you use Oracle, be careful. The reasoning they do is, the reason, oh, this is so weird and so rare, why would we fix that? Yeah, so, I mean, for a database company, it's always difficult to argue, or should we fix something that's already used in production? Yeah, because it might be that if we fix it, it actually breaks something. Yeah, that's a weird argumentation, but it may happen. Yeah? So say, no, we rather don't touch the stuff, and that may lead to problems. You can find discussions on that on the internet if you're interested. Okay. So concurrency control is awesome. Yes? It allows you to fully automate concurrent access to your database without having to worry about low-level thread synchronization mechanisms. And this is awesome. Isolation, most database systems guarantee atomicity and isolation for transactions. Concurrent execution of transactions increases the performance of these systems enormously without creating problems. Be careful with isolation levels. Make sure to set it to serializable. So I think we don't have to go through that, but the best summary of this lecture, I think, is still this one. Maybe I can show it to you here. This was done by a professor from Berkeley, database professor, and summarizing what we did today.
I remember when X-Ray and Y-Road.
Can you hear it?
There was something so confusing about that race. Basic operations kind of conflicts in the database. When the headline, it's all fine, yeah, it all makes sense. The serious sketch is alright, you know. Just too slow.
Okay, big data engineering. Actually, I was in contact with it. It's done by Joe Hellerstein. The name is not on the video, but everyone knows it's Joe Hellerstein, the database professor from Berkeley, one of the database professors. And because I couldn't find the video yesterday. And then I said, hey, what the heck? Did you take it offline? Come on, why? And they said, no, it's still there. You just search for crazy concurrency. You find, oh, cool, yeah, I'm right. And they're just planning other videos, and I also made suggestions for more videos, so maybe there's more to come. Yeah, with that, let's call it a day. See you next week. Yeah?